Okay, well, I think we've got a few more folks kind of trickling in, but we'll go ahead and get started here right on the hour just to make sure that we've got plenty of time for our guest speaker and for discussion today. So welcome back. It's been 2 weeks since we were all together, but I'm happy to see everyone again this morning. And we've missed you. I hope if you had the opportunity to have a spring break, you had a nice spring break. Here at Virginia Tech, I was telling last week to Andrea, we didn't have a regular spring break week this year. The university chose to take those 5 days and just pepper them throughout the semester. So I think the students have not really seen the same spring break that they would have normally looked forward to. But hopefully the intent was to keep everyone safe and healthy. And so hopefully that has worked out well. So to get started here today, just a couple of announcements and reminders for us. So we will have a reflection due on today's guest presentation. So please get that turned in by about close of business tomorrow, same form that we always use. Also next week, I think part 2 of the cold call assignment is due. So hopefully, I know that you've all reached out at least initially on that, and hopefully you're following up. So now's the time to do so if you have not already. And then next week, we'll have another guest presentation from NIOSH. Randy Reed at NIOSH will be joining us to talk about ventilation and dust control. So those are my announcements for today. Of course, if you have any questions, please do reach out to myself or Dr. Bricky, and we'll be happy to get back with you. But from here, I'm going to turn it over actually to Juan Jose, who's going to introduce our guest speaker today. So please do, if you've got questions and such, I know that we'll be happy to take those. So please either raise your hand or wait till the end. But Juan, you want to go ahead and get us started?
Okay, thank you. So good morning, all. Today's talk has been coordinated in collaboration with the American Rock Mechanics Association Student Chapter here at Virginia Tech. And we have a very special guest. He is Willian Joughin. He is an engineering consultant in rock engineering and has 30 years of experience in the field of underground rock engineering and includes 10 years in South African deep-level gold mines and 10 years of consulting. He specializes in underground rock engineering investigation and design and provides consultancy for services for mining projects on 6 continents with various ore bodies, geometries, and rock mass characteristics. His expertise encompasses geotechnical investigations, numerical modeling, mining method selection, design of mining excavations, investigation of shaft stability, and geotechnical risk. William has a special interest in deep, high-stress mining and seismic risk. He has published over 50 articles on rock engineering and is the recipient of the SIME Gold Medal and the Alec Wilson Award for the outstanding papers. William is the past president of the South African National Institute of Rock Engineering and past vice president for the African International Society of Rock Mechanics. He's the junior vice president of the Southern African Institute of Mining and Metallurgy. So today, William's gonna talk about the importance of uncertainty and risk in rock engineering design, which ultimately impacts worker safety. So William, thank you very much for your time. We really appreciate you being here. So go ahead. And the floor is all yours. Thank you.
Thank you, Juan, for that introduction. And thank you to both Emily and Juan for inviting me to do this lecture. So I'll be talking about dealing with uncertainty and risk in rock engineering design and essentially introducing you to a risk-based approach to rock engineering design. This work was done in collaboration with Johan Wessler from the Australian Centre for Geomechanics and some others. But Johan played a significant part in it, so it's important to acknowledge him. The reference material for this work, it's been published in this book. This book was published at the beginning of last year. It's called Ground Support for Underground Mines, and the editors are Yves Potvin and John Hadjigeorgiou. It's published by the Australian Centre for Geomechanics, and there are 3 chapters that cover the work that I'll be dealing with today. So the first chapter deals with the philosophy of probability, risk, and design, and the second one is an application, which is really my area. And then there's an appendix which goes through detailed probabilistic risk calculations. So this is where you can get the book at the Australian Centre for Geomechanics. There are some papers that are already in the, so this was, this you can get off the ACG website, the 2017 paper. It does not include the safety aspects of it though. The other two papers are updated, but perhaps a little bit more difficult to get hold of. Just want to acknowledge this work was done under a sub-project of the Ground Support Systems Optimization Research, which was led by the Australian Centre for Geomechanics. And I just want to acknowledge all the participants. We also, Ivan Platz kindly allowed us to use data from one of their projects. And of course, I'd like to acknowledge the sponsors. So I'll be talking, first of all, about just introducing you to uncertainty and variability in geotechnical data. And then I will talk briefly about probabilistic of modeling of stress damage. That's quite a big topic, but I'm just going to cover it briefly. And the key points that I'll be covering are defining some risk-based design acceptance criteria, and then applying a damage risk model, and then developing an economic risk model, a safety risk model, and then talk about the interpretation of the model results at the end, and then I'll provide a conclusion. So the context of this, it's a conceptual study, just a situation with long hole stoping and post filling. Just looking at one sub-level essentially, and we're looking at the potential for stress damage. And on the top right corner, you can see extreme stress damage in a tunnel. So firstly, we talk about aleatory variability, which is simply the random variations or the natural variability occurring in the world, and that includes natural variability in rock mass properties. And then epistemic uncertainty. This is the unknown or lack of knowledge and insufficient data, measurement errors, sampling bias, load uncertainty, model simplifications and assumptions all contribute to epistemic uncertainty. So it's important to note that a high degree of epistemic uncertainty is expected in geotechnical design, and therefore subjective engineering judgment is unavoidable. And this is a quote from Vic in 2002. He talks about the relative frequency approach, which is the more conventional approach to probability and risk, where the probability of an uncertain event is its relative frequency of occurrence in repeated trials or experimental sampling of the outcome. But the subjective degree of belief approach is essentially the probability of an uncertain event is the quantified measure of one's belief in the confidence in the outcome according to their state of knowledge at the time it is being assessed. Okay, and I'll go through this. So normally at the start of any underground project, you would collect data, and characterize the rock mass. And so on the left-hand side, you can see a very competent core in the tray at the top, and then some slightly jointed core in the middle, and then highly altered and broken rock in the lowest core tray. So we naturally have considerable variability, and we need to understand the spatial variability across the area of interest. We need to collect joint data, orientation, and all sorts of information. And in the early stages of a project, you always have a limited amount of information, so there's a lot more uncertainty. And in the early stages of a project, you might not have actually characterized your full variability and spatial variability across the area. And the variability and uncertainty in your rock mass properties. So for numerical modeling, we typically use the GSI, the results of triaxial tests and UCS tests. And this indicates the variability there. And often we start off the project with insufficient data. There is always a sampling bias because of the method that we use for testing. We have to select a sample of a certain size, which means that if you've got quite variable material and some weak material, you're always going to be sampling the better material. We often have measurement errors. It's important to check to see whether there's correlation between the different variables when you do probabilistic analyses, to see whether there's a strong correlation between the rock mass characteristics and the intact rock properties, for example. And you need to establish confidence intervals as you gain more data. And I think that Bayesian statistics is a good approach to dealing with this. And there's some excellent papers that have been published by Luis Fernando Contreras. And an important point to note is that particularly when you've got insufficient data, you need to apply some engineering judgment in the process. In stress measurements, we have quite a high degree of uncertainty. I mean, firstly, because you have a limited number of measurements. Usually the measurements are obtained from overcoring. Normally you can only do that once you have access to underground. You can do acoustic emission stress testing from borehole core, but it's a challenging process, and it is quite possible that you're going to have errors in your stress measurements, and you might, if you do a number of stress measurements, you often find there's quite a lot of variability, and whether that is real and natural variability or whether it is errors in the testing, you need to think about that. Horizontal stress is always a little bit more unknown and more variable. Your vertical stress is typically equivalent to the density times G times the depth, and there should be very low variability in your vertical stress, but the horizontal stress, it could vary significantly depending on local conditions. So you may want to incorporate quite a large standard deviation for the magnitude of your stress, and also the direction of your principal stress is also is something that can vary or could be incorrectly measured, and so you need to do sensitivity analyses, and in your probabilistic analyses you can take into account again quite a large standard deviation to deal with that. So the first probabilistic stress damage analysis that I'll discuss is based on the principle of elastic superposition, and this is covered in a paper that was published by Johan Wessler at a grant support conference in Sweden in 2016. And here we basically taken the output from MAT3D, a boundary element, fictitious force elastic model, and we varied the stress and the UCS and the GSI. And in this process, we use unit stresses to characterize that represent the stress tensor, And then the results of the analyses are imported into a program called MXWrap, which has been developed by the Australian Centre for Geomechanics. And in that, we can do a Monte Carlo simulation taking into account the stress uncertainty and the variability of the UCS and the GSI. And so these contours that are represented here, so this is on the top right is the decline, that is probability of failure presented there, and you can estimate the probability of the depth of failure exceeding a certain value using this. And then at the bottom right represents the crosscuts, and there are 3 crosscuts here, and you've got quite a high probability of damage adjacent to the stope, which is important to note. It's particularly relevant to this to this analysis. Then we also covered a number of elastoplastic stress damage analyses. So this was just a simple 2-dimensional cross-section, and through a single excavation. So generally speaking, a Monte Carlo simulation is not practical currently because of the time it takes to compute the analyses. So there are other probabilistic methods which may be more appropriate, where you need to run fewer models in order to achieve the results. And the point estimate method is quite well known. The response surface method, there have been quite a number of papers published recently using this. It's a very rigorous method, but it involves more models that need to be run. And the final one is the response influence factor, which is it requires the least number of models to be run for the amount of variables, and it's a very effective approach. And I don't want to go into great detail on these different methods. I'm presenting here the response influence method. So you have essentially you need to run, if you have 3 variables, you would need to run 7 analyses. So it's 2 times the number of variables plus 1, because you have a base case where you take the mean of each variable, and then you take the minus 1 standard deviation and plus 1 standard deviation for each variable, while keeping the other variables. You use the mean value, and in this approach, once you've done the analyses, you actually do you fit curves to look at the response, and then run a Monte Carlo simulation on those results. And it's a very effective way and a very efficient method of analysis. Of course, in the Itasca codes, you can, with Fish and Python, it's quite easy to build this into it. These are FLAC 3D models representing a 2D cross section, and the procedure was written up in Fish. The rock science codes have built-in functions for the point estimate methods and for Monte Carlo and in Latin hypercube. I haven't personally used the Monte Carlo and Latin hypercube in RS2, but the computational times are certainly becoming faster, and if your model is not too complex, then I suppose it is feasible. But you need to run about 1,000 iterations in order to get your results. And then we take the results of that, and I'm interested in the deformation. So I want to know what is the probability of the deformation exceeding a certain value. You could take the deformation results directly from the model, but does your model actually take into account the bulking and rotation adequately. So in this case, we've used an empirical approach. So we take the depth of failure and we multiply that by a bulking factor. And this was published in the Canadian Rockburst Handbook in 1996. Peter Kaiser does have an update of these bulking factors that has been published in a more recent text. And you get more deformation if you have light support for the same depth of failure, and yielding support will fall somewhere in between. And if you have strong, stiff support, then you get the least amount of bulking and deformation. So these curves represent the probability of exceedance of a certain deformation for the wall and the back and the floor for these three support categories. So now the big question is, what do you do with these results? So once you've got a probability of failure, what does it mean? So we need to define some probabilistic design acceptance criteria. So the first question I need to ask is, when is my design good enough? And how will I know? What confidence can I have in my design? And what do these results mean in the real world? So this, and in a deterministic analysis, you would simply look at the factor of safety, which is capacity over demand. But the probability of failure represents the probability of a factor of safety being greater than 1, typically, and the risk is the probability of an event multiplied by the consequence of the event. And it's, risk forms the basis for engineering design acceptance, whether it's explicitly quantified or not. I'm not going to go through this design wheel. I guess you can look at it in your own time, and just in the interest of time, and I'll get right down to it. So in defining probabilistic acceptance criteria, this requires some collaboration between the geotechnical design team and the owner or management. So the responsibility of the geotechnical design team is to collect the geotechnical data, interpret data, and construct idealized geotechnical models, including probabilistic parameter models of variability and uncertainty, and conceptual design of different alternatives. So for a factor of safety design, that you can do that in isolation. You choose upper and lower acceptance levels for FS criteria, and then perform your design assessment. But for probability of failure, you first need to define those acceptance levels, and that requires that interaction with the owner and the management. So it's a responsibility of the owner and the management to define the corporate risk profile and define the acceptance level for economic and safety risk. And then the process of determining the probability of failure threshold is done in collaboration. So that's quite an important part. And the risk models that I'll be presenting now help to close that gap and provide some sort of communication between the geotechnical engineer and management. So for economic risk acceptance levels, most big corporates have defined corporate matrices. And this is a typical one. We have consequence severity on the horizontal and the likelihood on the vertical axis. And these figures would be, I guess, appropriate for a fairly large operation. So we can categorize the risk according to this. I think for the type of analysis that I want to do, it's quite important to actually put numbers to the likelihood and severity. So we can't just use generic terms like highly probable or very likely, or we need to say to express a frequency. So this is daily, monthly, annually, 1 in 10 years, or 1 in 100 years, and then amounts for each of the consequent severity. So financial losses associated with damage to excavations may include rehabilitation costs, lost revenue due to production delays, equipment repair or replacement costs. Now, I've highlighted the lost revenue due to production delays in red because this is the most significant cost. So if you have any delay and that prevents you from generating revenue, that has the biggest impact on the operation because they are unable to achieve the revenue that they expect to achieve. And the frequency and extent of stress damage and size of rockfalls can vary significantly, and the resulting losses can range from insignificant to catastrophic. And in the decision process, we're trying to maximize shareholder value, and that's a risk-reward balance. Now, safety risk acceptance levels, this is now a very different concept. Most operations have an objective or a mission to achieve zero harm. Now, is there zero risk? I don't think zero risk exists. So everything that we do involves some degree of risk. And whatever we do should be reasonably safe, and we should be continually striving towards zero harm. And we need to evaluate the risk to the individual. So that is the risk to any person working on an operation. And then we also need to evaluate the societal risk. So the societal risk is the effect on the workforce. So so we're looking at the risk of having any fatality on the operation. And just to put things in context, this is a table that represents the average risk of death to an individual from various human-caused and natural accidents. And this comes from the United States Nuclear Regulatory Commission. So just to get an indication of the numbers, for a motor vehicle accident, we're looking at about 2.5 times 10 to the minus 4. It's quite interesting. The Australian numbers come out very similar to that. In South Africa, we're probably about an order of magnitude higher than that. So the falls, drowning, firearms, air travel, and so on. So you would expect air travel to be a lot safer. So that's 1 times 10 to the minus 5. And then there are other risks such as lightning, hurricanes, and all accidents would be about 6.3 times 10 to the minus 4. So this is an approach that was presented by Joughin et al. In 2003. And he quotes Bonnen, Blist, and Freyerling. And the concept, he introduces this policy factor, beta. And your individual risk should be less than beta times 10 to the minus 4. And we look at different risk categories. So when people are doing work that is completely voluntary and they're getting a direct benefit out of it, that policy factor would be 100. And it moves down to involuntary, and where we get where we may get some benefit or no benefit at all, and we have limited control in preventing an incident. So just for example, this is the UK Health and Safety Act executive applies a beta of 10 for voluntary to workers at a nuclear facility, while assigning a B equals 0.101 involuntary to the public. So the quite far extremes for that tolerate a higher level of risk for people who are choosing to work in the factory. But in the mining, we need to assume involuntary risk for the mining workforce unless it can be shown that the individual was empowered and cognitively able to consciously accept the risk in exchange for perceived reward. And this was quoted by Tebrugge et al. And interestingly enough, they chose an acceptance level of 10 to the minus 4, which would effectively equate, they suggested that, and that would equate to a beta of 1. And this was also published in the large open pit guidelines. But Joughin, my colleague Joughin, is suggesting, and this is also influenced by the Hong Kong guidelines, that an acceptance level for individual risk of fatality of 10 to the minus 5 to 10 to the minus 6 is perhaps more appropriate. But I don't think that should be the geotechnical engineer's decision. I think this is the executive's decision. This decision needs to be made by the executive, and it should be in line with what the expectations are, societal expectations are. So the societal risk, we need to look at the evaluation to the society. And the one way of looking at it, for a good example, that means you have a public exposure when there's a failure of a tank. The public is really at risk from underground excavations, etc. There's a great course that we need to consider. And this is an FN chart.
William, I think your audio is cutting out. Uh-oh.
Yeah, it seems he's maybe experiencing some internet challenges.
Hold on one second, guys. Let's see. Stop that video.
There we go.
And we're back.
Well, William, you're still muted, but we can see you.
Yes.
Okay, apologies for that. I seem to have lost the connection, and I think I need to share my screen again. I think I'm taking a bit longer than I should be, so I'll try and move through this quicker. Can you see the presentation currently?
We can.
Okay, I just need to organize my screen. Okay, so these are the various guidelines, and on the left-hand side of the curve, we've got annual frequency of what we have on the horizontal axis: 1 or more fatalities, 10 or more, 100 or more fatalities. So these, and we use this ALARP concept. And the ALARP concepts, if we have an accepted risk level, which is as low as reasonably practical, and if you fall in this zone, then you should be reducing risk as far as possible. If you're below the lower acceptance level, then you should be providing measures to ensure that the risk remains below that level. But if you're above that accepted risk level, it's unacceptable. So this is my colleague Joughin has used these guidelines from the Hong Kong Planning Department and then applied them to, I think I've skipped a slide, or it's missing. Okay, I'll just. So these are upper acceptance levels. So they represent the upper level, and they calculated for different lengths of exposure. And the lower acceptance level will typically be an order of magnitude lower. So we typically use beta equals 0.1 for the upper level and 0.01 for the lower level. So the same beta that I presented earlier. So this was calculated for a underground exposure of, for example, in a tunnel of those distances as indicated there. So, and these we applied these in our analyses. So if we come back to the analyses, I have a damage risk model. So I look at, in a scenario, I look at 3 different types of excavations, and I looked at the potential damage. LP represents the length of potential damage, and the individual squares represent the variability in rock mass characteristics. So it's a discrete interval across the length of the tunnel. And my model represents the probability of failure in any one of these discrete intervals. So if I take that concept, I can apply I can use a cumulative binomial distribution. So this is a very simple function in Excel. It's you can just apply it there, and this is we can say, so for a given probability of failure, so this is an extreme probability of failure, the top curve of 50%, down to a probability of failure of 1%. We have different curves of probability versus length of damage. So it's the probability of having either 0 segments damage, 1 segment damage, or 4 segment damage, 9 segments, for example. And these segments need not necessarily be contiguous, but they would have an impact. So we can number of lengths of potential damage that I
wonder if maybe we should turn off maybe the video is creating some challenges. Oh, there he is.
Sorry, you got to go through it again.
we might stop your just video feed, William, and see if that will help the bandwidth that you, if it's there.
Yeah. Okay. All right. Can you all see it?
We can.
Okay, good. So we need to get the time component in here. So we've now converted, as I say, this probability to a frequency. And then I need to look at the consequences. So if I have damage in my decline, I'm going to affect all the production immediately. So it has quite a significant consequence. If I have it in my footwall drive, it may only affect a third of the production, and you might have some flexibility built into the system, so it may not be immediate. And your crosscuts, if you've got a number of stopes available, you might have some flexibility built into the system, so that would also, you would have more time before you lose production, and it only affects a single stope. So we can quite easily then develop a model to calculate the rehabilitation cost per meter that is damaged. And then we can calculate the lost production, which is essentially the days lost multiplied by the revenue per day. And the days lost is essentially the time it takes to rehabilitate and get that excavation operational again. And so that's how we deal with the economic risk. And then those frequency damage, cumulative frequency damage curves can then be converted and plotted onto this. So we multiply them by the cost. So these are risk profiles for different probabilities of failure. So, we're trying to define acceptance criteria. So what we're looking at here is that if our guideline is we don't want to tolerate more than moderate economic risk, then we would select a probability of failure of 2% in this particular case. And then I'll quickly skip through. You can see for the crosscut, the curve shifts to the left and down. All the curves shift to the left and down because of the different profile. And if I could probably, for the moderate, I can get away with a slightly less than a 10% probability of failure in the crosscut to manage my economic risk. And the crosscuts, we have many, many crosscuts, so we have much higher frequency of damage, but the severity of the damage is far less. So the curve moves to the left, the curves move to the left and up. And again, our moderate, the green curve falls within the moderate risk, and we could select a criteria of 10%. But that's just the economic risk, and this is just quickly comparing the three graphs. But when we look at safety risk, we need, I've made an assumption that because the damage does not necessarily represent a rockfall, because not all the bolts will necessarily fail, particularly if you have a good ground support system in place. That number, I don't know exactly what it is, and that's something that would be nice to know. But so we can now determine the probability of having a rockfall that affects a certain number of tunnel segments. So a rockfall across a certain length of tunnel. Effectively, that's what I wanted to get to. And then I need to look at the temporal and spatial coincidence. So the spatial coincidence is being in the wrong place, and the temporal coincidence is being at the wrong time, being there at the wrong time. So we look at the amount of time that people expend in the exposure area to look at the temporal coincidence. And the spatial coincidence is simply the damage length divided by the exposure length. So it's really just the probability of being in the wrong place at the wrong time. And then you can take into account risk mitigation in the model. So monitoring, if you're doing very good monitoring, and there are very good techniques these days with SLAM technologies, simultaneous laser and mapping, or LiDAR and mapping, and you can get closure measurements and determine whether your support is under risk and whether there's a risk of a rockfall, and you can stop and rehabilitate. And that can be used to mitigate. So if you've got very effective mitigation, you can apply a low factor for monitoring. And then the vulnerability, if you've got a mechanized environment, people will be some distance away, perhaps, and working under a canopy, so they might have some protection, which can be used. So you can build your mining safety principles into the safety risk model, and then it's simply and then looking at the exposure analysis, you need to do a detailed analysis to look at where people are exposed and how much time they're spending in those different areas. So we might have unprotected personnel coming to map a face or to do a survey or something like that, but they have a very low exposure. They don't spend a lot of time there. But you might have an operator, you'll have an operator working in a vehicle that will be protected, but they will spend a lot of time in those areas. And you'll have people traveling. And so there are equations presented to build an exposure model, to build a safety risk exposure model, and the equations presented in the book. And so in the same way, I can plot these probability of exceeding any more fatalities in 1 year. So I have these curves that represent that, and there's in an environment where you don't have a lot of people working in one place at a time, it's unlikely that you're going to have a large number of fatalities. In a South African mine, you might have 10 people in a particular working place at one time, so these curves will be a lot flatter, and you're more likely to have 10 people trapped or killed, so you would have a much flatter curve that would extend out. So these curves represent the societal risk curves. and the little dots on the left-hand axis represent the maximum individual risk for a particular situation. So in this case, my societal risk as well is within the ARMA region, but I need to make sure that I have that my my individual safety risk, with a 10% probability of failure, I'm actually dropping below. I'm dropping below the 1 times 10 to the minus 5. So I could get away with the 10% probability of failure and still meet my safety criteria. However, my economic risk criteria says 2%. So I would be using my economic risk to make a decision in this situation. So in the footwall drive, I apply the same principle, but now I need to be less than 5%. So while my economic risk criteria says 10%, this needs to be less than 5. And then for my in my crosscuts, here I also need to get at least below 5%, but even my societal risk is really quite close to the upper limit. So maybe I would even want to drop it more, but that would obviously add additional costs. Because you want to, if you're in the LARP region, as I mentioned before, you'd actually want to move. You want to be trying to strive to move down. So you would be trying to do things either by minimizing exposure of people, or by putting more support, or by changing your design. So the top 2 graphs represent your acceptance criteria. So for the interpretation of the decline, my economic risk criteria is 2, safety is 10%, so I'm going to choose 2%. There's my 2% graph. So I need to choose a support system that is capable of absorbing. If I choose a stiff support system in my in the back, I would need to it would need to be able to accommodate it would need to be accommodate looks like about 20 millimeters of deformation, and then for the wall it would need to be able to accommodate about 50 millimeters of deformation. So even though it's stiff, it needs to have some ductility in the support system. So, and then here for the footwall drive, I'm going to use, I said I needed less than 5%, so I've chosen 4% to look at that criteria. And when I get to the crosscut, I have a bit of a problem because my walls continue to deform, but it's the portion of adjacent to the stope. And the way to deal with that actually is to do just-in-time mining. So you only develop that crosscut after the adjacent stope has been backfilled and filled, and then it actually won't see that amount of deformation. So there are ways of getting around it. So that brings me to the end, and I'll just do my conclusions quickly. So this process, it is applicable for geotechnical analysis and design, and takes into account geotechnical uncertainty. And the understanding of aleatory variability can be improved by collecting more data and improving the quality of data through training and control. And then as your project gets more advanced and as you're implementing, you would get a much better understanding. So stress and model and uncertainty remain a challenge. So there's always going to be some subjective engineering judgment required. And we need to incorporate both economic and safety risk in our criteria. So at the start, I talked about the relative frequency approach, which is used by the insurance industry. For example, where you have large amounts of data available and it is possible to assess the potential risk quite reliably. But when you're dealing with more uncertainty and you have high consequences of events that don't occur frequently, it's absolutely necessary to incorporate a subjective degree of belief approach. And if you've got good data, that'll improve the confidence in the outcome and the degree of belief, but the interpretation remains subjective. And I think that's it. I think that's all I have. And apologies if I've gone over time.
No, you're fine. Thank you.
Mm.
So do we have questions?
Yeah, this is William speaking. I have quite a few questions. I don't know if you can hear me or not.
We can hear you.
Yeah.
So just for down.
William?
We can't hear you
Yeah.
anymore,
Yeah,
William.
you're really breaking up. Is there a way that you could maybe type your question? I know that's probably a long question, but your internet seems to be very spotty.
Sure, yeah, I'll type it out.
Or if you can maybe try turning off your video as well.
Yeah, yeah.
Okay, can you hear me clear now?
That sounds a little better. Yep.
Okay.
Now we lost it.
Okay. In the
Yeah.
meantime, are there other questions?
Hello, I would like to ask a question to William. So how do you see these risk-based design approaches being broadly implemented in the industry? Like considering that maybe regulations are gonna get more strict or are getting stricter like in many countries. So do you think this is something that is gonna have to be implemented for all mining in all the scales, or do you think this is something that just the biggest companies that are actually concerned or that have an actual concern on safety are going to implement?
Well, at the moment, it's certainly, it's only really applied in situations that are potentially high risk and not well understood. So, and it's certainly when we've done this type of work, it's been large corporates that have asked us to do a special study to look at a particular risk situation, and then we will evaluate it both from an economic and a safety perspective. So this approach that we've tried to make a little bit more generic, it certainly has not been widely adopted yet. The large open pit guidelines include the FN chart and that safety risk acceptance criteria. So there are some companies that are starting to apply that for their safety risk acceptance criteria currently.
Mm-hmm.
I hope that answered your question.
Thank you. It does.
So I see that we've got a question here from Judith that says, how does the risk level affect insurance?
Yeah, I haven't tried to calculate that directly. I guess it has an indirect effect. I mean, if you have if you have either high economic risk or high safety risk, that will affect your insurance premiums. So certainly your insurers would be looking at your safety statistics and particularly you're insuring against economic risk. So if you have frequent incidents of high consequence, then that would significantly influence your premiums. So I guess there's a fairly good relationship between that corporate risk matrix and the interpretation of your insurance of the insurers.
I think William is busy typing out a question as well. Are there other questions before he gets his in? William, I was going to ask how How at present does this get, and maybe you could just speak to the South African case, but how does risk at present, is it taken into your licensing or permitting of the mine in terms of the safety risk that's presented by excavations? So how is that currently done, and how would using more of the models that you're putting forth, how would that perhaps change that licensing?
That's a good question. I'm not sure that it would affect the licensing directly. I'm just it doesn't seem to come into the licensing of for operations. It would affect the. I mean, if mines have accidents, then obviously there will be inquiries in them, and the mine may stop work on the operation. So they may stop the operation for a period of time until they're happy that the mine has done something acceptable to deal with it. So it's normally a short-term delay. If there was a major incident, they might close the mine permanently. So that's what would happen, but not. Yeah, I guess, I don't know, I guess that answers it in a roundabout way, I hope.
Is there currently a factor of safety approach in terms of the mine design, and that's what's used to satisfy for the licensing requirements?
Yes, normally in terms of permitting, it doesn't really come into it. It comes more into the raising of finance. You would need to do a proper feasibility study, which needs to be accepted, and you need to take safety into consideration in that.
Mm-hmm. Okay. I don't see William Heasley back on yet. Other questions from the group?
So I may want to ask again, I'm sorry. So my question is, like, I think these approaches that you are proposing are very in line with the philosophy of the ground control management plans. That is something that in Australia they have been trying to implement and trying to maybe make general in the industry. So do you think that if the ground control management plans are something that gets implemented globally to provide or to prevent accidents due to ground control failures, do you think that could be like a great tool to also start to implement more like these sorts of approaches?
Yeah, in South Africa, we have something equivalent. We call it a code of practice to combat rockfalls and rock bursts or other risks, but it has the same purpose as a ground control management plan. So we've certainly been doing that for 20 years or longer, 25 years. I understand in Canada they also call it a ground control management plan. I'm not sure in the US. What do you have something equivalent here? I think. I reviewed some of the coal mines. I think the MSHA is a lot more prescriptive. Mm-hmm. That was my impression, that MSHA is much more prescriptive than you. They define the guidelines and they give you a permit to operate. I think, is that correct?
Mm-hmm. Yeah, in coal industry, they have the roof control plans, but it's not as explicit, or it is not as clear, or the elements that it should contain are not as thorough as the ones that are required in Australia.
Yeah. Mm-hmm. I definitely got the impression that MSHA is a lot more prescriptive, whereas in South Africa, the responsibility is placed on the mine to identify risks and to put in systems in place to address those risks. And if something goes wrong, then that code of practice, which is equivalent to ground control plan, gets called in, and then it gets reviewed, checked to see whether it adequately addresses that particular risk. And usually there's some changes that are made, or at the very least, there are changes to the implementation of that system.
Yeah, I think that's a fair a fair assessment of the way that we do a lot of things health and safety wise here, is that MSHA is quite prescriptive, and we don't have the same risk-based approaches that it sounds like you have in South Africa, and certainly that I'm more familiar with in Australia. So we are almost at time. So I think, you know, I know some folks have to hop off and get to other classes. Certainly, William, I want to thank you so much for joining us today and talking to us about this important topic. I think issues of risk assessment and risk management and design are important to all the different facets of mining and minerals. So thank you for sharing with us. I'm certainly able to hang around for a few more minutes if you'd like to stay on, William, or if anyone else would. But in the interest of time, could we just offer William a great virtual round of applause and thank him for being here? And certainly we do appreciate it.
Well, thanks very much for the opportunity. Yeah.
Yes, thank you very much.
Thank you very much. Great presentation.
Take care.
Thank you.
Thanks.
Yeah, I'll share the PowerPoint presentation as well.
Okay.
Yeah.
Thank you so much. Yes, I or Andrea will get out to the rest of the class. If you would share that just by email to either me or Juan, that would be great. And I will also get the link to the recording to you.
Okay.
Very
Thank you.
good.
Perfect.
So I think, yeah, was there anything else, Juan, that we needed to take care of today? We're probably keeping William from getting dinner or something.
Yeah, no, I think it's fine. I have a bunch of questions, but I think it's good. I may email you some other ones, but thank you very much for your time. It was a great presentation, and I'm very interested in these topics. Thank you.
Yeah, thank you.
All right, guys, I hope you have a great afternoon, and you have a good evening.
Thanks.
All right.
Okay.
Take care and thank you.
Bye-bye.
Cheers. Bye.
Bye.